And And of course, the big one today is we have the SciANN, which is a TensorFlow API for scientific computations and neural networks. So, whoops, why? There we go. Of course, I want to share this with you first. You should have gotten an email from our Design Safe team regarding a survey. If you have not seen that email, please click on the link, or you can just follow this QR code and take the survey. We really appreciate the feedback we get on these Design Safe webinars, and these surveys are a great tool for us to give you more webinars and redirect how you would like to see fit. So thanks again. This is kind of what the Design Safe community is all about, so I appreciate it. So yeah, today we were talking about the SciANN, which is a TensorFlow API for scientific computations and neural networks. I think everybody understands the importance that neural networks and deep learning has played in computation, right? Image classification, computer vision, search engines, recommendation systems, speech recognition, autonomous driving, healthcare. It has made a great impact everywhere. And of course, it's made a huge impact in the natural hazards world as well. And so we bring to you today Dr. Ishan Hagigat, hopefully I pronounced that correctly. He is from the University of British Columbia, where he's a postdoctoral fellow, and he's studying stochastic modeling and uncertainty quantification in engineering systems. Before that, he was a postdoctoral associate at MIT, and he's been looking at stochastic modeling and machine learning, and he's bringing that expertise with him to this webinar. I'd also like to note that after this webinar, we will be holding a workshop where you get actually hands-on on the technologies that Dr. Hagigat is going to be explaining and talking about. That is going to be in its own Zoom session. So when this Zoom is over, we'll start the next Zoom, which is going to be the workshop. And the link to that is posted in the chat. And again, we will share that link at the end of today's webinar as well. So with that, I'm going to be handing this off to Dr. Ishan Hagigat. Thank you so much for joining us today. Very much looking forward to listening to you present this. Thank you. Let me stop my share and you should be ready to go.
Thank you, Charlie, for the introduction. Let me share my screen and then put the screen. Can you see my screen?
Yes.
Yeah, it looks great. Thank you.
Perfect. Hi, everyone. Thanks for joining this webinar. My name is SciANN Hagigat, and in this presentation, where is the laser? Okay, yes. In this presentation, I will talk about neural networks, physics-informed neural networks, and also the package that I developed during my work in this area, SciANN. And hopefully you enjoy it. Before I start, I would like to thank all of my collaborators so far, and which talking with them, collaborating on different projects with them resulted in this package SciANN. The main motivation for this work is the recent kind of explosion of application of deep learning in engineering, especially after Google open source TensorFlow in 2015 and made it available to everyone, and the advertisement and the hype around that and the opportunity actually around that. So a lot of groups started using deep learning in the beginning as a data-driven tool. So if you have an experiment, you would like to represent it with neural networks and do some predictions or kind of use neural network as a regression tool. Some people used it for detecting earthquakes and so on. Some groups started using it as a representation for kind of simulations from finite elements. So you have a set of finite element simulations, then you want to replace it with a neural network so that you can evaluated very fast. A set of very recent works are they're trying to use neural network and data-driven tools to invert partial differential equations governing the systems. And the most important one that caught our attention and a lot of others is this work by Raisi, Perdikaris, and Karniadakis, which they introduced the concept of physics-informed neural network. And it received a lot of attention. I think now has over 2,000 or so citations. And the reason is that they introduced a framework that if you have no data, you can start with fully physics constraint problem, like a boundary value problem. If you have a lot of data, you can tune the weight of each last term, so just go fully data-driven. But most importantly, if you have a little bit data and some physics, then it allows you to solve the system, invert the parameters, and do some predictions. And that would be a part of this talk today. And why SciANN? So first of all, in scientific computations or in many engineerings, we have engineering applications. We do certain things like curve fitting, regression, solving integral equations or differential equations. So these are certain specific tasks that, for example, the input variables to the network are specific in a way, the output are specific, the objectives are very specific. So machine learning tools, however, they are very general. So they are mostly designed in the beginning, especially it was mostly about image processing and natural language processing and other applications. So more like a classification tool rather than regression tool, gradually used for regression and so on. But still, since the framework is general, you have to spend a lot of time. I had to spend when I started working on this learning TensorFlow. It has a very steep learning rate, and I had to spend a lot of time setting up a TensorFlow model or Keras model and initialization of the parameters and so on. So there was a lot of pieces that you had to put together to be able to do some machine learning. And I realized when I was started working in this topic in 2018, that maybe if my codes are just growing and growing. So as a way to organize my codes, I started making it as a package, and then eventually we released it in 2019. And really, after we published or archived the paper, it received some more attention, and we are now working on different parts of it. So the outline of today's talk is, first of all, deep learning and neural networks. Some of you may know, but I will give an introduction for everyone. The physics-informed machine learning, and I will also present some applications, some that I have done, also a very nice study by Ken from UCLA, from Professor Brandenburg group. He will present his work. I really like what he did for classification of soils. And then we will also discuss some challenges and opportunities in terms of research in this topic. And then, as Charlie mentioned, the second part would be a workshop. We will do a hands-on practice using SciANN. And please don't forget to copy that link and use the new link that is posted for the workshop. And if you have questions, I have these kind of breaks. So if you have questions, please post it as you find something not clear, and I will try to address it during the talk or at the end. So deep learning is a subclass of machine learning which uses neural networks or deep neural networks, or even can be recurrent networks and many more complexities as an approximation tool. So like any other numerical method, deep learning also has two sides. One is we want to construct an approximation space. Essentially, we have a field variable, let's say temperature distribution in the United States, but we don't know the true function representing that distribution, and we want to approximate it. So that's the first part. And the second part is now we want to find the parameters of that as approximation for a specific task. So it's very similar to many classical methods in a way. Let's say linear regression, right? So we approximate that, or we hypothesize that the system's response is linear. And the parameters of this representation is A0 and A1. Therefore, we need a training algorithm or a solution method or a least square method. All these things that we have been using in scientific computing to find these parameters. So we can do quadratic regression, or we can have it as a more complex general neural network. So it's really a way, or a modern way, of constructing functions. And I will show you that with the modern frameworks, you don't need actually to have a complex neural network for your problem. Even if you have a linear regression problem, but you have a very large data set, let's say a few million data points, you can still use efficient structure of this TensorFlow to do a linear regression, because they can handle large data sets, they can distribute the training and so on. So that's the part that we do. We first approximate our space, and it's very important. If you have a quadratic data, a data that follows some quadratic train, and if you just use a linear regression, it's not sufficient. This is the same with neural networks. If your data has a specific architecture, the architecture that you pick here can affect the performance of the trained network. So the second part, so first we construct the neural network. The second part is how to find the parameters. I'm interested in regression type problems, whether it's solution of PDEs, ODEs, whether it's curve fitting. Therefore, mean squared error is the most popular approach, which comes as maximization of likelihood function. But also there are other types that has been discussed in design safe seminars, more focused on classification tasks or image processing. But here we are more focused on the scientific computations. Therefore, mean squared error would be used. So that's a measure of error. We want to minimize this, or we want to find parameters of a network such that it minimizes this loss function. The most popular approach is a gradient descent optimization. So essentially, you have the parameters of the network updated during different iterations by this kind of in this direction, in the direction of the gradient of loss with respect to network parameters. And I will explain briefly that a lot of problems actually comes from this first order approximation. So this is the classical method, whether how you pick alpha and gamma. There are a variety of methods. And then if you use the training on the full data set, or if you use small batches, that takes you from a stochastic gradient to conjugate gradient methods. But the overall approach is this. So just from this slide, I want you to know that two sides: construction of functional spaces and then optimization. Okay, so for instance, I mentioned that you can construct a linear regression with neural network. So if you have just one output, and then with a set of parameters take you, one input with a set of parameters take you to the output, that's a linear regression. Or quadratic regression, you can, what they call in the machine learning community, you can do feature augmentation. So instead of x, you can also have x squared or x cubed or so on as an input, and therefore you can construct kind of polynomial approximations. Or the simplest neural network would be a single layer neural network, a single hidden layer. And essentially, this would be the simplest architecture that was introduced long ago with a sigmoid activation function. And it was shown that this architecture can approximate any measurable function. It was shown quite a few decades ago that can approximate any measurable function. And if the training is not successful, it's either due to bad optimization or lack of enough training data. So that's proven mathematically. A more general representation of neural networks, we have a set of features we can make a linear combination of them. Every node in this graph represents a linear combination followed by passing through an activation function. So from the inputs, you create these linear combinations, and then you pass it through a nonlinear activation function. You get the output, you get multiple outputs for different nodes, and that would be the input for the next layer. So it is like a compositional structure, f of g of so on, of x eventually. So this compositional structure is known as deeply connected or densely connected neural networks or feed-forward network. There are other variants too, like recurrence and convolutions, and I will not cover those here. And some of them are not directly applicable for reasons that we're going to see. But the overall approach is this. For example, for image classification, every feature is a pixel of an image or a convolution of a set of pixels, essentially. And every data point is just one image. And we are interested to whether detect some objects in it or whether to classify the whole image or part of the image and so on. So that would be a classical neural network now for ImageNet and other architectures. A more interesting construction that we might be more interested in engineering is to construct, for example, displacement as a function of a space and time, or temperature as a function of a space and time. So the inputs can be time and space, and the outputs can be physical parameters. And when you look at this image, so this can be treated as an image. Early works of neural network was like this. Even if you have a finite element, you treat every slide as an image, and you train it on a previous architecture, or you can construct these continuous forms. So you would be a continuous function of time and space. So we essentially want to fit a network that represents the whole solution here. And the data points are different points of this image. So this is a more interesting architecture because of the reasons that we're going to see in a second. So now this has a functional form, right? So you can think about neural networks in general as just a function. So you can, if you have a fracture, you can use classical approaches to continuous and discontinuous functional space. You can use Heaviside essentially here. Or if you have, I don't know, a weak discontinuity, meaning that discontinuity presents in the derivative, but not the actual temperature, for instance, or displacement, for instance, you can use sign distance function to construct such a function. So it is just another function. And we have used it, for example, for bimaterial problems. So just think about it that way. I'm going to go back here for a second. So this way of representing neural networks just shows the connection between different nodes of this network. It is not the actual implementation. So this shows that X, for example, passes information to these nodes. But what this node does is the actual algorithm behind the scene. And that is shown here. So the parameters are, or the TensorFlow parameters are represented in these red fonts, and the rest are inputs, right? So every node in the actual computational graph is an operation. For example, is a summation, is a multiplication, is a subtraction, and so on. So it is an operation, and it has two inputs and one output. And if you define the architecture this way, then this allows us to do a lot more. For example, we know that from the chain rule, we know that what is the differentiation of A times B. We know that it's differentiation of A times B plus A times differentiation of B. So this allows us to automate a lot of processes. And this has been one of the main reasons of successful stories of neural network, which is an algorithm that is called AUTOGRAD, or automatic differentiation. So this helps us to now to have many layers, because now this automatic differentiation algorithm can follow this graph and can do the derivatives for us, which is needed for the training. Also, it can be parallelized heavily because if you observe here, this operation is independent of this operation. So they can done on in parallel, and then they can add it together later on. So this is the graph-based implementation was really important, which was happened, I think, in Theano as the first package, and later on in TensorFlow. Every neural network framework now, or deep learning framework now, has such implementation. So as a result, now you can do an algorithm that is called backpropagation, or it is essentially chain rule, and you can do it efficiently. So you start from the end, that's why it's called backpropagation. So that derivative, if we are interested in the derivative of loss with respect to parameters to do the gradient descent optimization, therefore, you can start from the end, so gradient of loss with respect to the output of 5 with respect to A0, and then so on and so on, and trace this. And you can factorize a lot of operations and so on, because everything is pre-computed on the graph. So, and it turns out that also we can use this automatic differentiation to take derivative of loss functions or any really network output with respect to x's, y's. This is more interesting for us who like to represent systems with differential equations. So we can now take derivative of displacement, for example, with respect to x, and that is a strain or other properties. And this is the point of physics-informed neural networks. Okay, so now that takes us, as a general introduction to neural network, takes us to physics-informed neural networks. So essentially, this was the work of this paper, of which they introduced this concept of physics-informed neural network. So two features that I just explained. One, if we construct the function in a way that the inputs are space and time, and then the outputs are physical quantities. Two, the use of automatic differentiation. So if that construction allows us to take differentiation of, for example, displacement with respect to x, or velocity with respect to x, and so on. And therefore, we can evaluate a PDE residual of interest. So we can evaluate it, we can measure how much error this network has on that partial differential equation, and we can include it in the loss function so that the optimizer minimizes the PDE itself. They also showed that you can do inversion. So you can have parameters of the partial differential equation as network parameters, and if you have data, then they will be optimized for. So before that, there are also a set of works. They use neural networks for solving PDEs, but they use it in a classical discrete form. So the features are not continuous space and time. They don't use automatic differentiation and so on. So there are a lot of pieces that you may think, okay, it's just easier to do a finite element. But in this continuous form, now it gets interesting because now you can do many more with it. So I will show a few cases later on. And also it comes with some other challenges that we're gonna discuss. So for example, for an elasticity problem, let's say you have a two-dimensional problem. So the features or independent variables are x and y. You can define a network for displacement or for hysteresis. You can also define network parameters for lambda mu, the shear modulus and Lamé constant. And the total loss function would be if you have data for displacement or if you have boundary condition for displacement. So that would be one term. The same for other terms here. So if any data that you have comes here, if you have a momentum equation, you would like to impose it, you can impose it with automatic differentiation, and that would be included in the loss function. So optimizer minimizes not only data, but also the momentum equation. And you can include constitutive relations, and you can use it to actually find the parameters of the network. And the interesting part is that each term, you can also introduce a lambda. And if you have a lot of data, physics is probably not important anymore. Then you can have the lambda to very small value and then just use the data-driven part. If you don't have any data, you can start as a boundary value problem, like a finite element solve. And as data come in, readjust the weights so that the data becomes more important. So that's the interesting part of this architecture. It is very active area of research. So the first paper came not long ago, but there are different variations to address different concerns with this method. Fractional pins, variational pins. There are more optimal architectures like adaptive activation functions. There is the discretized form of this approach to kind of domain decomposition, X-pins. There are also some suggestions to solve some of the challenges associated with this that we're going to discuss. But for example, two of these suggestions are gradient scaling, because it's a multi-objective problem. So we have different loss terms. We want to minimize ideally all of them, but each one has a different landscape. Therefore, the gradients are different and the distribution of the gradients are different. And this work proposes a gradient scaling to be able to train all the terms equally. And also neural tangent kernel. And we also introduced a non-local variation of pins. The point is that it's an active area of research, and it may change significantly in the next 2 or 3 years as the approach evolves. That takes us to SciANN. Let me see if there is any questions so far.
There are a few questions, Ehsan. Do you want to answer them as we go, or wait until the end?
Maybe we answer one, and then if it doesn't take time, I don't know, we can start with one.
Sure. So Ali Safwan asks, in pins, any idea how we should pick the optimal activation function? Is it just trial and error? And then also, how can we define our own activation function? Can you show us a real example?
I will discuss this later on, but really, so far, it's been trial and error, depending on the problem. We pick the right activation function. But a very recent work, this came out about a month or 2 months ago now, that's neural tangent kernel. Eigenvalues of this kernel tell us whether we are using the right architecture or not, and why one network architecture works better than the other. So at the moment, still everyone uses try and error. The most popular one is 10H, but it's not the best one for different problems. But this particular work also may be helpful to find which network architecture is the best. So maybe I think we can continue, because some of the questions I see that they may be addressed in later slides. So I will get back to the questions at the end then. So now on the SciANN, so as I said, when I started working on this, I gradually converted it to a package so that everyone can use it. And the reason is there are a lot of pieces other than setting up the architecture or activation functions and so on that everyone talks about. The initialization of the network itself may be bad, and that may result into not being able to train the network. And in fact, in another work related to NTK, they show that if the initialization does not follow certain rule, you can never train a neural network. So there are a lot of challenges that I faced, and it took months to learn them, and that's why it resulted in SciANN. So now let me show you how we can use SciANN to solve, for example, this partial differential equation. This is the Berger's problem, a hyperbolic equation with regularization term and subjected to these boundary conditions. So this is, there is no labeled data. We just want to solve this problem using neural networks or physics-informed neural networks, really. Okay, so the first part, as I briefly explained, is construction of approximation space. And that's all it takes in SciANN to do that. So essentially, you identify the independent variables of the system, x and t, for instance, are here. You define them with this variable interface. And then the ultimate variable that you are interested about, which is the fluid velocity in this case. So that is defined with this functional interface. So u would be functional. The first character here is a way for me to trace the computational graph and be able to do the automatic differentiation and so on. So it's important to use this notation. The second one is the inputs to this kind of neural network. So that's up to here, we are constructing u as a function of t and x. And then if we don't put anything else, that's a linear regression. If we put 8 times 20 neuron, that's like an 8-layer neural network with 20 neurons each. 10h is the activation function. And there are many more things that we can use with this function also. All of them are interfaced here, and you can just add different keywords to set up more complex architectures like ResNet and so on. So this would be the first part in SciANN to be done with the construction of neural network. The second part is the optimization problem. So now in the math module in SciANN, we can import, for example, differentiation, sign, and so on. The first objective function we have is this differential equation. So we would like to find the parameters of this network, this functional, such that it satisfies this partial differential equation. So the first loss function is diff of u with respect to t, and so on. So just typing this loss function as it is. And so all of the graph-based operations are handled within this diff interface. And then we may have also the boundary condition. So we want also because this PDE has a trivial solution. The trivial solution for the PDE is just 0. So we want also to learn the PDE such that it imposes these boundary conditions. So initial condition at t equal to 0, u should be minus of sine pi x. So that's done here. And then at the boundaries, u should be 0. So I use here the sign convention that was the early implementations. Now you can just type t equal to 0 and x equal to 0, and it does the right setup for you. So that's the optimization constraints. Now we can define the optimizer. So optimizer is done with the Sci model. The independent variables are x and t. And then we want to minimize L1, C1, C2, C3, all of them together. And by default, it's a mean squared optimization using Adam optimizer. You can also change that here. So and this is the second part. So once the optimization is set up, now we can do the training. And it's just m.train does that for you. And x data and t data are just a set of collocation points randomly picked in this domain so that the optimizer can minimize these losses on that set of data points. And we want all of them to be as close as possible to 0. So that's the setup in SciANN to solve, for example, such a problem. And at the end, if you evaluate u, once training is completed, if you evaluate u on a set of points, then that's the solution you would get. So this example is shared in our GitHub. Some of the examples we do in the workshop. And just a reminder that you need to, after the end of this session, we will change a Zoom session to a workshop type so that we can do a hands-on practice. There are also other keywords that you can use. For example, you can log functionals, meaning that you can log the progress of training, for example, at different frequencies and so on. Everything with just one keyboard, you can get a lot of outputs out of this. And just some statistics of SciANN. So as I said, since we archived the paper, it was originally open source in 2019, but since we archived the paper in, I think, April 2020, and there has been a lot of views of the documentation website and also a lot of downloads. So only last month it was over 1,000, and then our paper is also among the top downloads of my favorite journal, CMAME, which makes it exciting. So one last slide on the implementation details. So just to have a connection between how different classes in SciANN are connected with TensorFlow and Keras. So essentially variable is the input layer there, but set in a specific way for scientific computations, X, Y, T, and so on. Functional is like the dense layers or recurrent layers and so on. And again, it is implemented in a specific way to handle that and automate a lot of initialization and setup that goes here. The math operators, they are all set up using the lambda layers of Keras, and that allows us to trace a lot of operations and do operator overloading. So you can multiply variables, you can subtract, and everything is correctly shown. We can also, this part is the neural network setup, and then optimization setup, and then the final optimization model that sets up the weights and all the other things that goes with the optimizer, and then you can do the training. So just an example of how the standard regression and physics-informed regression can change the accuracy of solution. So let's say you have a data set, you have a cloud of points that are distributed here, and we would like to fit a neural network to represent it. This is the true function. We don't know it, of course, we just have the points. We want to represent it. Well, we assume we don't know it, but we know it. So we want to represent that cloud of points with neural networks. So it's few lines, you set it up on using SciANN, and that's the error you get once the network is trained. We can evaluate it and find test grid and see how we are performing. Now, this equation, we know that it satisfies this parabolic differential equation. So on the same set of data points, same neural network architecture, same activation function, if we impose this differential equation, now you can see that the error immediately drops, and drops significantly compared to this one. So the performance improves significantly on the same data. And that's the interesting part. Of course, if you have infinite data points, we don't really need such an operation. But this was, I think, on a relatively coarse grid of 20 points in X, 20 points in Y. Therefore, the grid itself is not large enough to have a multi-layer neural network representing it. But the physics improves the predictability significantly. So that is a kind of comparison between the regression type problems and how we can also think about incorporating physics and so on. So now that takes us to some applications. The first one we looked at, just experimenting and so on. We looked at this elasticity problem, so subjected to these boundary conditions, and also these complex body forces. And just to get a pattern, essentially. And so we solved this as a forward solver, so no data, like the Berger's equation I showed you, subjected to boundary conditions. You can solve this. We solved it as an inversion problem. So assuming that you have displacement field, I don't know, from digital image correlation or some other approach, then can we set up a neural network to find the parameters? And the answer is yes, with the physics-informed architecture, and we find the parameters that accurately represents this. We also along the way introduced, and these are also implemented in SciANN, that you can use transfer learning. So you can train the network on one problem, on one, for instance, shear modulus, and that takes, let's say, long, I don't know, 3,000 epochs or 4,000 epochs. And but if you have a similar problem, just the parameters are changing, you can just save the weights and you can just pass it to the new network and retrain the weights for that new parameter. And it takes far less iterations to get to the same level of accuracy. So this is done also very easily in SciANN. You can also construct, that was a very important part of our paper, you can construct surrogate models as a using PINN very efficiently. So not only, so now I told you how you can include, how you can construct, for example, displacement as a function of x and y. It would be wonderful if we have displacement as a function of x and y and, for example, shear modulus. So that is more like an analytical solution that by changing shear modulus, you get a different solution. And physics informed is very efficient in that regard. Only 4 data points on shear modulus, but imposing the physical conditions, we can construct a network that remains accurate for a wide range of shear moduluses. And this is very practical for engineering applications, because otherwise we had to do different finite element simulations every time we had a change in elasticity modulus. We used it on a more complex setup. So let's say this plate under tension, under tensile extension. And so for a set of parameters, and displacement is fixed, so all of them are subjected to a fixed displacement, but the elasticity modulus and yield stress are changing. So different variations may result into a fully elastic region or a kind of elasto-plastic region with a sharp localization of plastic strain. And the solution is very different between these two, as you can see, especially for the plastic strain. And it's very sharp in this regard. But so we set up a physics-informed surrogate model only with 9 data points out of this table. These cross ones are the training points. But we set up the physics, all the plasticity and elasticity constraints, and we test it on all these circles. And first of all, without the surrogate modeling, for example, training on the on a reference solution takes a lot of epochs, but then retraining using transfer learning takes far less epochs, and it remains very accurate. So this is inversion for a wide range of values. With elasticity, we had a little bit more error, but the point was this transfer learning had been very advantageous. And the error in the elasticity really is because of the particular feature of this problem, that once the plasticity evolves, you have this very sharp shear band. This is the surrogate model. So this is the mean squared error, or L2 norm of error in displacement as a function of yield stress and elasticity modulus. So you can see that, and this is the L2 norm of the solution at all points. So it's not just one point. So you can see that it remains very accurate for a wide range of parameters just by 9 data points. This is impossible with just data driven. So you need far more data points to be able to train an accurate network. But physics, because of the derivatives and how they are connected together, can help us here. So now I think Ken has something to show us. Ken?
Yeah.
Let me stop here.
Okay, let me share mine. I'm Ken Hudson, and I'm a PhD student at UCLA working with Scott Brandenburg. And so I've used some of the used SciANN for this little project that I did that we were working on together. And I'm going to first give a brief introduction into what this problem is and why we're trying to solve it with SciANN and machine learning and neural networks, and then show the results. So first, consolidation is a common problem in geotechnical engineering. This is when you have a clayey soil and you add a load onto it. Here's just kind of a simplified view of it. You're adding a load onto the top surface of your clay soil. And over time, that clay soil compresses. And it's compressing because water is getting squeezed out of the pore space between the clay minerals. And so what we can do is we have this big differential equation that governs the response in a one-dimensional system of the settlement of the clay. And Scott Brandenburg implemented a Pi consolidation, which is iConsol, which he converted then into Python, called PyConsol. It was originally in Java, which is just a code that solves this differential equation using finite differences. And let's see. So what it takes is, first of all, there's some general input parameters, such as the initial stress at the top of the layer, what you want the convergence tolerance to be, the unit weight of water, atmospheric pressure, and if water can drain out of the top or bottom or both of the soil layer. And then it also takes all these soil properties, such as what is the thickness of the clay, how many number of elements are there, what is the compression indices, which tells you kind of the rate at which it'll have volumetric change when it's being loaded or unloaded, and a bunch of other different properties of the soil itself relating to consolidation and what are needed to solve this differential equation. So we have this, this physics-based model, but what's interesting is that a lot of the time we run these tests where we take a sample of clay and we put loads on it, and we measure the settlement of the clay with time, and we want to back out from that settlement with time profile. We want to figure out these soil properties so that we can go ahead with design of building like a structure on that clay or something in the field. And so we have to kind of do it backwards. We have to know, we'll know the settlement with time, which is like this curve that's shown here. As time goes and different loads are being placed on the soil, we're getting these jumps in settlement. We want to know from this what are the soil properties? What are the compression indices? What are the coefficient of permeability of the soil? We want to be able to get all those out. And so this is where SciANN can come in. If we can train a neural network that reads this settlement with time profile and knows the loading sequence and other things, then it can return to us the properties that we want to use for our site and our design. And so for instance, this is stage one, meaning that you put a load on the soil and it settled, and then it kind of finishes all of its settlement and flattens out. And then we add another stage of loading, another stage of loading, and then we do some stages where we unload, take some weight off so that we can see how it reacts when it's being unloaded and reloaded. So to be able to train the neural network, we wanted to run PyConsol a lot of times with lots of different soil parameters input into it, and then generate those settlement with time as simulated out of PyConsol, and then train a neural network using those data. And so we had to come up with a range of input parameters that would be representative of most clayey soils. And so we took a lot of these as just uniform distributions. For example, the virgin compression index was taken between 0.2 and 1.2, randomly sampled in a uniform distribution there. The recompression index is taken as 5 to 20% of the virgin compression index. It's usually somewhere in that range. And so that is randomly sampled within that, but it's related to the C sub C. And so we come up with all these different properties that you can see here that all kind of eventually get related back to each other in some way, but it allows us to come up with a range of properties that are realistic to simulate. And so, for instance, this is the parameter space of the compression index, virgin compression versus the recompression index shown against each other. So you can see that kind of range in values that are being simulated. So what we did was we produced 10,000 of each of these input parameters that are all, so that each individual test has all these related parameters. And we ran those 10,000 simulations in PyConsol in a Jupyter notebook. And a few of them were unable to converge, 659, so it wasn't a full 10,000 simulations that were used as the training data set. But what that output, right, is the settlement with time. And so we discretized that settlement with time profile by taking 5 settlement values that are evenly spaced in log time within each stage, so that we had 45 for each simulation, and used those as the features for the neural network training. So here's a plot showing like those data points. So here's that first stage. So we're taking 1, 2, 3, 4, 5. And those are evenly spaced in log space so that we kind of get all these different points along the settlement curve. And then the second stage and the third stage and so on and so forth. We get 5 points from within each stage that'll be representative of the settlement profile. And then we used labels in quotes. We used 5 soil parameters as those defining labels for each for the training. And so the 5 that were chosen to be probably the most impactful were C sub C, C sub R, C sub K, C sub alpha, and Tref. So we trained the neural network, and after we trained it, then we did a test of the model. And so we produced 1,000 more simulations that were totally independent of the training data set, but within the same data range as the training data set. And we took those settlement profiles that were output, and we predicted the 5 soil parameters based on their settlement time values that were output. And you can see here, these are each of the 5 parameters, and the x-axis is showing the actual value that was used to simulate the data, the testing data in PyConsol, and then the y-axis is what was predicted using the neural network, using the output from PyConsol. So you can see overall, it's doing a fairly good job. If it were a perfect prediction, it would always be 1-to-1. And so it's doing really well, especially this one Tref parameter. Well, most of the parameters are doing well. And so
thank you very much, Ken. So just 2 questions here. How many parameters you have? And I guess the point is that it is very difficult to come up with a functional form, I don't know, a linear or quadratic with this many data points and this amount of nonlinearity. So the point is that a neural network can help you in this regard when you don't know the functional forms. How many input parameters you had here? And we can move to the other slides because we have to go to the workshop too.
Yeah. Yeah, there were 5 soil parameters that were used as the what was being predicted from, and 45 input features from each settlement.
Excellent. Excellent. Thank you very much. So just I want to go a little bit faster to finalize this slide. We also proposed a non-local architecture using dynamic differential operator. So essentially, the classical form of neural network is f as a function of x, but you can also consider non-locality. And this is also implemented in SciANN and can be used readily. So I will not discuss these, but essentially it allows us to account for more dependence of these, more accuracy essentially in terms of the output of the neural network. So the standard networks, they stop at this level of accuracy, whereas the non-local one, you can go far beyond that. On the activation function, one person asked, and I think this slide is very informative, that for instance, if you have a vibration problem, we know that it's a mixture of sine waves, for instance. When you use a tangent hyperbolic and you train it on this shaded area, it is accurate, but it never becomes predictive. As soon as you go out of that range, the results are not accurate. But when you use a right activation function, so the neural network itself is general, but just the activation function, because we know that it's a wave, if you use its sign, then we can see that it's also capturing some features for prediction. So note that no classical method you can do this. So in the, I don't know, ODE or PDE solvers, mostly they are discrete. So you don't know how to go other than those discrete points, whether you have to first fit and do a curve fitting and then do extrapolation or so on. But this architecture, which has, for example, u as a function of, as a continuous function of time and x, allows you to do even go beyond that and test whether your post prediction or your kind of extrapolations are accurate enough. We have used it also for some more complex problems with Dr. Wahed from KFUPM. So how much time do we have, Scott, for the workshop? Can we go another 2-3 minutes for, because the challenges I think also important.
Yeah, and there are some questions too, but it's your show, Ehsan. So if you want to go to the workshop now, that's fine. If you'd like to answer some questions, that's good too.
So let me just quickly review these in 1 minute, and then maybe we can also answer a few questions when we are moving to the workshop. One note here that the training is not necessarily fast. So if you compare a forward solve with finite element and neural network, the training is not even comparable in most cases. At the moment, and one reason is first order optimization, which is getting improved. Now they are Google, both Google and Tensor and Microsoft, and I think Facebook with PyTorch, they are working on second order methods to make them more optimal. The network architecture plays a role here, and also some problems they are just we are not able to train it with neural networks. And one reason is multi-objective optimization, but one other reason can be a stiff problem. So these are now known problems. For instance, there was a discussion by about a spectral bias of neural networks. So the average solution can be trained very fast in the first few iterations, but then in order to get to high frequency solution, you need a lot of epochs. So and these are more like challenges that are faced now, and also research opportunities. So there is the hyperbolic equation and so on. So we can discuss them maybe later after the workshop if we found time. But gradient scaling is a very efficient way to deal with multi-objective optimization, and it is implemented in SciANN. So you can just activate it, and I will show you how. And also, learning rate sometimes plays an important role. If you are training and you see immediately it diverges, probably there is something with the equations if you don't know it in advance, and controlling the learning rate is a way to identify the source of that problem. Okay, so I stopped here. These are a summary of the previous comments I made, and maybe a few questions, and we can log into the design safe system for the workshop.
All right, great. I'll go through a few questions, but let me know when you want to move on to the workshop, Ihsan. So
Okay.
we have 9 questions. I don't think there's probably enough time to answer all of these. So I'll just go through them in the order they came in.
Yeah.
The first one, in slide 16, could you explain the constant shift between exact and predicted pressure?
Slide 16, so I have to oh, here. Yeah, so that's a good point. So there is no constraint on pressure here, as you see, and they discuss it in their paper that all these governing equations, they are imposing some relation between the gradients of the pressure, not the absolute value of the pressure. Therefore, the absolute value based on these constraints are irrelevant. But if you know pressure at one point, you can fix it, and then that would give you to the right value. So the bias is the one that is shifting this, and it is not controlled by this set of equations. That was the reason here.
Okay, thanks. The next one are lambda and mu properties of the medium. I think that's Lemay constant and shear modulus. And if yes, how are they output from the network?
These are network parameters. You can also make them a function of x and y. You can define some stochastic variation for them. And that just makes the inversion more complex. So the simplest one is just to have them as constant, and that is in SciANN is done with the interface parameter. But we will experiment with one of these. And maybe one more, last one.
One more before we move on? Okay. So for different ranges of data, what will you suggest, since the answer may not be convergent due to different ranges of different sets of data?
Yeah, so in SciANN, we also going to experiment this because of the operator overloading. We can do everything. Actually, let me discuss this, but briefly, it's all about how you scale and rescale your data, and make sure that the part that is neural network parameters, they have a mean of 0, roughly 0, and a standard deviation of roughly 1. So you can put a lot of operations before this entry level, and you can put a lot of operations before the last, after this exit, to scale it back to your true values, whatever those are. But in between, the most optimal way is to have data and input and output that have a roughly mean 0 and a standard deviation 1. Okay.
All right. Thanks a lot,
Excellent.
Ihsan, for this this webinar. And I think that Charlie will show a slide to close it out before we move on to the workshop in just a minute.
So I will stop here.
And share. Great, once again, Ishan, thank you so much for joining us today. Actually looking forward to the workshop part. Once again, here's the details on the workshop. Oops, I realized my camera is not on. There's the details on the workshop. We also copy and pasted that link into the chat. So please go ahead and join us there. If you need the meeting ID and the passcode, those are listed, of course. Once again, this webinar and this workshop will be posted after the recordings are complete in about 3 days. If you go to our training archive off of DesignSafe, you'll find those all listed there and be able to find those on the DesignSafe YouTube channel. Once again, here is the link for the survey. I please ask that you take the survey forward, as it really helps us plan these workshops and these webinars better for you. Thank you so much.
Thank you, Charlie. So I'm moving there.
Okay. There is a little question on the workshop is at 3 p.m. Central. I'm sorry, Natalie, does that mean it's going to be on at 3 p.m. an hour from now, or are we going to immediately start the workshop?
I thought we were immediately starting.
Okay, so the workshop is at 2 p.m. Central.
Yes,
Immediately
2 p.m.
following-
Central. Yep.
2
Okay.
Central, 3
Yeah, 2
Eastern.
Central.
Yeah.
Sorry.
Okay.
So
If
people
you
can
have
just
any
head over
questions-
there now. Yeah.
Yeah, we're gonna head over there right now. If you're looking for any help, find us on Slack. We'll be able to post the details to that in the general Slack channel as well. And once again, thank you so much, Ishan, for joining us today. We'll be going to the workshop now. We'll see you guys there. Thanks.